Okay, so what we're covering today is Chapter 11 and Chapter 12. Um, the first part of 11 is about atoms and the periodic table, and we're not covering the entire amount of material that's in there about the periodic table, um, but we will cover a little bit, and then we're going to do a tiny little bit on antimatter as part of this. Okay, so the first part is talking about how atoms are tiny, numerous, moving, ageless and ancient, or mostly empty. Okay, so what do we mean by that? Well, they are very, very tiny. And so right now, like in your fingernail, there are probably millions and millions of atoms. Every lungful of air that you breathe contains millions of atoms. So it's just, they're very tiny. And they are numerous, of course, because we fill the universe up with them a lot. And they're very ancient because they go back to the birth of the universe. Now, this picture here is an electron microscope photograph. And this round thing is not an atom, of course. But in the background here, you can see the material of the um, underneath, and you can see tiny little dots. Those basically, you are getting close to a picture of an atom there. Okay, so anyway, so yes, they are very, very tiny. This, by the way, is a tiny little machine part built by humans for tiny little nano machines. Okay, so they're ancient because they go back about 14 billion years. That's when the Big Bang happened at the start of our universe. And that's when the um, parts of the atom started to be made. Now, most of the atoms that started out in the universe were hydrogen with some helium. And then as they were combined uh, into higher value materials, so higher mass atoms by combining or fusing the atoms together. So the nucleus of the atoms were fused together. So you could put two hydrogens together and get two protons in the nucleus. You could put two more in there, and then you get four in the nucleus. Anyway, so the idea is that this is called nucleosynthesis. And nucleosynthesis is that idea of creating new nucleuses. And that happens inside stars, but a lot of higher mass atoms have to be created during a supernova explosion or collisions of stars. Now, atoms are mostly empty space. This picture is not at all accurate. If you think about the atom as being the size of a football field, well, the nucleus would be like a golf ball that you've put in the middle of the field. And the electrons would be like flies that are flying around in the football field. So yes, so it does not look the way it's shown in the picture. But that one is good for us to learn to understand that electrons go around a nucleus of an atom. Okay, now elements are materials that have only one kind of atom. So pure gold, for instance, has only gold atoms. There are, I need to update this, 118 types of atoms that are now named. 90 are found in nature, and the remainder are synthesized. So let's see if this has the updated number here. Yep, 118. Okay, so yes, we've been improving on nature by creating atoms in the lab. So now we have 118 atoms that we recognize, that we know their properties of. Um, so let's see. So the earliest civilizations had 12 substances that turned out to be elements. So gold and silver, lead, copper, tin, iron, carbon, sulfur, antimony, arsenic, bismuth, and mercury. Those were ones that people had actually refined down to the pure material. The first, but we don't know who did that. Who was the first person to refine copper? We don't know. The first element that we know when it was discovered was phosphorus, and that was discovered in 1669. And yes, from urine, many buckets of urine were refined down to find phosphorus. But then, as the scientific revolution occurred, a lot more elements were added every year. And so anyway, so people begin to figure out all the different elements that were out there. Now, what does an atom look like? Well, we talked about how it has a nucleus. The nucleus, of course, contains protons and neutrons, right? So protons and neutrons. The element is given a number based on the number of protons. So hydrogen is number 1 because it has 1 proton in its nucleus. Whereas helium is number 2, it has 2 protons in its nucleus. Now it also has 2 neutrons. So the mass of it is heavier than the hydrogen, which has usually no neutrons. If you add the mass of the protons and neutrons together, which we call nucleons because they're in the nucleus, then they make up what's called the mass number. So the atomic number is just the number of protons. So the atomic number of helium would be 2, but the mass number would be 4. And lithium has 3 protons. It's number 3. And again, it usually has 3 neutrons, so its mass number would be 6. And aluminum has 13 electrons and 13 protons in its nucleus, but it usually has more neutrons. So it might have 14, 15, 16 neutrons in there. You need more neutrons to help hold the atom together. We'll talk about that. Okay, so here's a periodic table that has not been updated because it needs to go out to 118. Okay, so I need to get the newer periodic table. Let me see if I... okay, all right. So anyway, so I need to put a newer periodic table in here. Now, so what's going on is that around 90 of them are natural. So of course, something like uranium is natural, right? Thorium, plutonium, those are natural. But then we get into the ones that were created by humans. And one of those is number 95, which is AM for Americium because it was created in America. And then we have 96, which was named for Madame Curie, so that's curium. And then we have 97 and 98, which were created in Berkeley, California. And I used to work at the lab in Berkeley, and I would overlook where they were making new elements. So my lab window looked down on them. 99 is called Einsteinium, and 100 is fermium for Fermi, who Fermi Lab is named after, and it's Fermi was one of the people who helped develop nuclear energy. And then we have Mendeleev, for Mendeleev, who is the creator of the periodic table. Sorry, there's also Mendel, who is a scientist, but that's not named for him. Okay, so Mendeleevium and Nobelium and Lawrencium. Anyway, for Lawrence Berkeley Lab, which is where the elements were being created. So anyway, so those are new ones, and then we have these other ones here along here, which are also have been created. And they're named for various people or places, locations where they were discovered. Okay, but natural elements usually are around 90, 92. Okay. So anyway, so yeah, so every time you have a new proton in the nucleus, that makes a new element. And when you get a new proton, you get a new electron that is attracted. So lithium has 3 protons. Usually it has 3 neutrons, and usually it also has 3 electrons if it is electrically neutral. So the positive charge of the protons and the negative charge of the electrons cancel out. And neutrons are, of course, always neutral. They have a 0 charge. Okay, so what's an isotope? An isotope is when you have atoms that are the same element. So they have the same number of protons, but they can have different numbers of neutrons. So different numbers of neutrons. Now, why are the neutrons in the nucleus of the atom anyway? Well, they help hold the atom together. The problem is positive charges want to repel. So if you've got a helium nucleus and it has 2 positive protons, then those are going to want to repel each other. And it helps to put in something else. So what you can put in, or what nature puts in, are neutrons. And neutrons have 0 charge, so they don't try to make the atom burst apart. And in fact, what they do is they help provide what are called gluons. Gluons are tiny little particle sort of things that jump around and sort of connect and the atoms, the protons and the neutrons together. And so those gluons jump around and they help from one atom to the other, and they pull them together. I said one nucleon to the other. Okay, so from a proton to a neutron, and from a proton to a proton. And so because of that, these help glue the atom together. That's why they're called gluons. So what happens is as you get an atom that gets larger and larger, the protons keep trying to repel each other. The nature keeps shoving in more neutrons to provide more gluons to hold the atom together. Protons and neutrons both have gluons, but the protons can't hold together just by themselves. They need some additional help from the gluons of the neutrons. Okay, and so that is what is happening there. So okay, so let's go back to isotopes. So there are neutrons, but you can have different numbers of neutrons. You just have to have enough to hold the atom together. Sometimes you don't have quite the right number. And in that case, the nucleus will break apart. And that's what a radioactive nucleus is. It has a number of neutrons that is not the right number to help it remain stable for billions of years. And instead, it will break down. Now, sometimes these radioactive elements break down after a day. Sometimes they break down after an hour. Sometimes they won't break down for millions of years. Okay, so isotopes of elements have different numbers of neutrons, and they also will have radioactive isotopes, and those can have different, what are called half-lives. The time it takes for half of them to radioactively decay. Anyway, so that makes some of them very useful. So if you want to build a nuclear reactor, you need some elements that are radioactive. So you need isotopes that are radioactive. So anyway, so how do we tell them apart? Well, we identify them by their mass number, right? Which is the protons plus the neutrons that are in the nucleus. Now, the thing is, these isotopes, they act like regular, they all act the same as the element. atom. They all chemically act the same, but they do break down radioactively different. And sometimes they are different by mass. So they only differ by mass, not by the electric charge. Okay, so let's go look at some of these. So when you're looking for neutrons in an isotope, then you take the mass number, which remember has protons plus neutrons, and you subtract away the atomic number, which is just the protons. Okay, and that should leave you with your neutrons. Okay, so let's look at some isotopes. So hydrogen actually has isotopes. Most hydrogen is hydrogen 1, like 99% of it. And it has one proton, because it's hydrogen, and it has no neutrons. And it, of course, has one electron if it's electrically neutral. But there is hydrogen 2. Okay, so this is their mass number here that we're looking at. It's the combination of the protons plus the neutrons. And so for hydrogen 2, it has one proton because that makes it hydrogen, but it also has one neutron in the nucleus. And of course, it has one electron. And there's even tritium, which is the name of hydrogen 3, which has one proton to make it hydrogen, but it has two neutrons and one electron. Okay, so hydrogen has 3 possible isotopes. And actually, they can be valuable. We use what's called heavy water to help control nuclear reactions. And the heavy water has more neutrons in it, so it's heavier. So it's using the isotope of H3 or H2 in the water molecule, which is H2O. So it's regular water, you can drink it and everything, but it does have more neutrons. But it's very, very rare. So most hydrogen just has one proton. Okay, now you may have heard of carbon dating. Well, what does that have to do with? Well, regular carbon is carbon-12. And carbon-12 has 6 protons and 6 neutrons. Oops, yes, and 6 electrons, right? 666 there. Okay, but sometimes you will have carbon-14. And there's even a carbon-13 too. But carbon-14 is the radioactive one that is used in dating of objects. So like you can take a piece of wood from a campfire that was found in a cave, and people can check and see, well, how old is this wood? Because it has carbon in it. And some of the carbon is carbon-14. And that starts to break down radioactively. So one can look at the ratios of the carbon-12 and the carbon-14, and you can check to see how old this object is by knowing how many carbon nucleuses have broken down. So anyway, so what is carbon-14? Well, 14 is its mass number. If I subtract away the 6 protons, that leaves 8 neutrons, right? But still has 6 electrons. And there is actually a carbon-13 also, which would have 6, 7, and 6. Now, sometimes you'll see this written as carbon, and they'll put the 12 up above and the 6 down below to remind you how many protons there are. Okay, so that's another way, oops, that this is written. Okay, so you could write hydrogen 2, 1, right? And hydrogen 3, 1, and hydrogen 1, 1. Okay, so that is another way of writing it that you'll see in the literature and books and things like that. Okay, but most of the time people are supposed to know how many protons there are, so you just have to say how many nucleons, the mass number. So we just say carbon-12. Okay, now when it comes to uranium, you could have something like uranium-235 or uranium-238, and those are radioactive. So, but they have different lifetimes. So they have various different uses. And so uranium is number 92 on the periodic table. Looking at this little crystal periodic table my husband got me. Okay. And of course, uranium is number 92. So that means there are an awful lot of neutrons because we had 238 for the mass, but only 92 are the protons. Okay, so that leaves 146 neutrons, but we still have only 92 electrons. Okay, so various isotopes of various materials. Some of them are radioactive, and that makes them useful in different ways. But they are, in fact, what was I going to say? They are useful in different ways, but we can define them, right, by how many neutrons. And usually the bigger the atom gets, the more neutrons you need to add in there. Okay, now, why is this important to you in your life? Well, you may have heard about agreements like the Iran agreement, where that had something to do with nuclear weapons creation, right? What it has to do with is that it was an agreement that Iran would not use its centrifuges to refine radioactive materials like uranium to the point where they could become a weapon. Because the thing is, because these isotopes are often very rare, the ones that you want, then you have to put it into a centrifuge, spin it around, and then the heavier materials go down to the bottom. So like uranium-238 will go down uranium-235, so it'll be further down. And then you take that and you take that little bit and you put it in another centrifuge, spin it again and again and again, and slowly you build up a heavier isotope, or you can select the isotope by this constant refinement. Anyway, it takes a lot of centrifuges, a lot of time to do that. And that's what the Iran agreement was about, was we had inspectors in there who were allowed to inspect that. So when the agreement was broken, we no longer had inspectors in to check on that. But that's why it's so difficult to actually make an atom bomb from scratch, is that you have to refine the radioactive material. Okay, so different elements, okay, have different properties. So hydrogen is more flammable than helium. So why did people put hydrogen in some airships like the Hindenburg? Well, hydrogen is more buoyant, but also at that time, helium was not available to all countries. And helium actually was discovered, well, in the sun first, and then we found it on Earth, but we found it on Earth in Kansas. And America would not sell helium to the Nazi Germany. And so that's one of the reasons that the German airship here, the Hindenburg, was filled with hydrogen. Okay, so it's important which element you use, which isotope of which element, and so people have to know something about the periodic table. Now, the periodic table is a listing of the known elements, but you don't have to memorize it. That doesn't mean you shouldn't memorize it. You could do it for fun. So you can say things like hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, etc., all in one breath. So yeah, it's kind of cool to keep it in your head a little bit and train your memory a little bit. But we do keep the periodic table around in various forms so that we can read it. Okay, so the periodic table has a lot of interesting things. Now, one of the reasons it's called the periodic table is it has periods. Periods are these rows, and the idea is that as you go along, properties reproduce periodically. So carbon here, number 6, and silicon have very similar properties. And those have similar properties to germanium. And so on, and tin down below that. So the properties get repeated. And so over here we've got beryllium and magnesium and calcium and strontium. Those have similar properties. And so that's why they're in columns or families. So anyway, so the periodic table has the elements in organized by increasing atomic number. There's 7 horizontal rows. Those are called the periods. And the properties have regular trends. The columns are called groups. They're like the families of elements that have common characteristics. Okay, now who figured this out? Well, we get our periodic table from Dmitry Mendeleev, and there were a lot of other people trying to figure out the periodic table at the time, or figure out some way of organizing elements. Nobody knew it was going to really come out to be a table exactly, but at that time, people were trying to figure out all the elements. Now, it's not that easy. I mean, we know what the elements are now, but that's because we've benefited. But just 100 years ago, there were still elements being discovered. And so over here, I've got some materials. So you can see how difficult it might be to tell one element from another. And so, for instance, maybe you recognize the purple of amethyst. That's quartz in there, silicon oxide. Next to it is something purple, but that's fluorite. The fluorite also comes in many colors, like quartz. So this green thing is fluorite too. But is that the same as this green thing? No, that green one is malachite. And malachite has copper in it. So here's actually an element that you might recognize. Here's some copper ore. And there was a picture at the beginning of the chapter which showed giant crystals of gypsum. And so here's some gypsum here. And sodalite, so where we get soda from. And here is an ore that actually contains gold. So green often means copper. This actually has gold inside it. And this one has a little bit of uranium. And here's some iron. And you can see it's attracting magnets and paper clips. And this is some calcite from a pool of steaming water. So anyway, so we've got all these wonderful elements, but they're all trapped usually in minerals with other types of atoms. And so people had to refine them and figure out what they were. Now, here I've got some different elements. So I've got some aluminum, titanium, iron, copper, and tungsten, some pure elements. And one thing you may notice is that the blocks have different sizes. Well, why is that? Well, because these blocks all have the same mass, but because the elements have different densities, then each cube is a different size. Okay, so density is one of the properties of elements. So copper, pure copper, has a certain density. And since it's very close to the block iron here in size, then those probably have about the same density. But then their color is very different, right? So people had to figure out, how can you even identify things? Aluminum has the largest block here. It's got the lowest density. Okay, so let's go back and look at some more stuff. Okay, so what was happening in the 1800s where people were making all these fantastic discoveries about different elements that they were refining and separating and figuring out a new element that they could not break down any further. And so what happened was that they started to publish all this data. And sometimes they would just write a letter to a friend and say, hey, I've discovered this stuff. I think it's a new element. It seems to have this density. And it also combines with oxygen in a 2-to-1 ratio. It combines with hydrogens in this ratio. And so they would talk about the mixture. They would talk about the color. And so there would be this information, and it would be published in journals. And it was just a mess because there are over 100 elements about. And so people were getting all this information, but there was no organization. Well, what happened was Dmitry Mendeleev and others were trying to figure out a way to organize this. And basically, Mendeleev put the elements information on cards, and he would lay them out in different ways and try to figure out some organizing property. And so everybody was kind of doing that. Mendeleev would sit on the train on the way to work and go through these in his head or lay out his cards. And eventually he came up with this. This is the original periodic table right here. So it doesn't look quite like the one we have today. For one thing, of course, there's a Russian up here because he was Russian. But also it's sideways to the one we use now. So you'll see here's hydrogen. There's no helium because it hadn't been discovered yet. But here's lithium. Okay, and in the modern periodic table, here's hydrogen, and lithium's right below it. Okay. But then also there's lithium, and then we have beryllium, boron, carbon, nitrogen, oxygen, fluorine. So that's pretty familiar. Here's beryllium, boron, carbon, nitrogen, oxygen, fluorine. So we had that part. Okay, and the thing is, when he got to the end there, he said, hey, and there's no neon yet, he said there should be another element here. It can't just keep continuing, because what he said was that, you know what, some of these elements have similar properties. So he put potassium underneath sodium because they had similar properties. And he put rubidium underneath there. And so you can see here we've got sodium, potassium, rubidium. And so he was putting these in the order of their properties. And that was what made his periodic table better than others. First, he started off with mass. So increasing mass, because again, they didn't have atomic numbers yet. They didn't know how many protons there were. And so he started off with mass, but then he started to say, okay, I've got to start a new row, or column in this case, because they have the same properties. So anyway, so he would assign the properties. Now, sometimes as he would go along, his rule, he would have to change it. He was trying to do things by mass, but you can see here, magnesium is 24, aluminum 27, silicon 28, right? So mass is increasing. But some places he would say, that doesn't seem right. So over here, he went from 122 to 128 and then to 127. He said because properties are more important than just the mass. So he ranked things by their properties. But also, because properties were more important, then sometimes if he was missing data, he would skip, because he would realize that arsenic here goes underneath phosphorus. Arsenic does not go under aluminum. They're not similar. So he figured out that there were two missing elements. So he put them in as question marks. And what made it really brilliant, too, was not only is he losing gaps, but he was saying, hey, I think there are two missing elements. And he said, here's what I think they're going to be like. So he would describe them. Because the hole they were in, he would know their properties. So he would say, I think it's going to have this density. I think it may be this color. It's going to combine with 2 hydrogens, and it will combine with 1 oxygen. And he would describe what he thought it would look like so that other people could discover it. And so his brilliance was that other people then went ahead and did discover these elements. So anyway, so that's how the periodic table started out, was him looking at the importance of the properties that repeat periodically. And why do they repeat periodically? Because of the number of electrons in the outer shell. Those are the ones that perform chemical reactions. And those are the properties that they were looking at. Okay, now, so when we're looking at the atomic mass, that's the mass of the protons, the neutrons, and the electrons. And you'll see that in the periodic table. We're not going to do too much with that. But the idea is that the mass of a proton is about 1.661 times 10 to the minus 24 grams. And that is about the mass of a neutron. Okay, so this is kind of an average number for the proton-neutron combination. And so that's how we figure out how we list things by their mass. So in the periodic table, you've got the atomic number is the number of protons. And then we have the atomic mass unit, which is protons, plus neutrons, and giving them a certain number of grams per mole. Okay, so Avogadro's number. We're not going to get into that. Anyway, but it's very useful. It tells you how many grams there are in 1 mole of the substance. Okay. Now, allotropes are fun. Allotropes are when you have 2 or more forms of the same element, but they have different bonding structures. So they have different physical appearances. So diamonds and graphite are the same material. They're both pure carbon. But the arrangement of the carbon atoms is different. So here are some pictures of some of the allotropes of carbon. So the diamond is this one, and the diamond is very, very strong because it makes full use of carbon's 4 bonds. So each carbon atom will cling to another one with 4 bonds in a tetrahedral structure. Makes it very, very strong. So a diamond is one of the hardest substances known. But graphite is weak. And why is graphite weak? Well, graphite makes these very strong rings. Sorry. Okay, so it has strong hexagonal rings with double bonds and stuff like that. But it uses up all its bonds, so it doesn't have any really to cling to any other layers. So there's just weak bonding between the layers. So when your pencil snaps, which has graphite, well, that's because those layers break off. But that's also why you write with a pencil. As you write with a pencil, what you're doing is rubbing off layers of this graphite onto your paper. Now, the buckyball over here was discovered not too long ago when someone said, hey, what does soot look like? Soot's not graphite, soot's not diamonds, but it's made from burned wood, so there must be some other form of carbon. So one of the forms they found was the buckyball, and its actual full name is Buckminster fullerene. Why would anybody name something so horrible? When they looked at it, the buckyball has 60 carbons, and you can see that it's got this beautiful arrangement. And people looked at it and said, that looks like a geodesic dome design, like they use for stadiums, how they put the girders in place to hold the stadium. And the designer of the geodesic dome was an architect named Buckminster Fuller. So his first name was Buckminster. His last name was Fuller. So they named it for the architect. So that's why it's called Buckminster fullerene, or buckyball for short. Now, graphene is when you just have one layer of the graphite. It turns out to have very different properties than graphite in general. So we're going to have a look at another slide on that. And also nanotubes. We'll talk about those too. So anyway, so carbon has 1, 2, 3, 4, 5, 6. No, 1, 2, 3, 4, 5, 6. No, 5 at least. Allotropes. Okay, so graphene is really cool. It's flexible. It's strong. It's 200 times as strong as steel for the same thickness. it also can be used as a semiconductor. So someday it may be that the graphene is like a piece of paper, your computer that you have in your pocket, and you can fold it up and stuff it in your pocket, because it also radiates heat better than silicon, so you wouldn't need all the fans and stuff. So, and because it's so strong, you wouldn't need a protective case. So it might be something very, very flexible. So anyway, there's lots of cool information about that online. Um, so anyway, so someday maybe graphene will be used. It's also waterproof. People envision you could wrap a boat in it. You could, um, uh, wrap anything in it. It's an incredible substance. Because it's so strong, you could use it on walls, right? And armor. It's got lots of applications. Another thing that has lots of applications are nanotubes. Nanotubes are carbons that are in a tube form, and it's kind of like a cannoli or something. You can stuff it with stuff. So here they've shoved a cesium atom inside there. And so the nanotubes, so here's a picture of actual nanotubes. They think they can use them to build structures. So tiny machines might be made of nanotubes. And also, when you squish a nanotube down, it's like a little spring effect that puts energy into it. So then it could be like stored energy where you have squashed nanotubes. So someday maybe those will be what makes your watch go, instead of charging it up electrically. You would just squish it down, and then that energy can come out as electricity. And they can be put in paint. They can be used in medicines. There are all sorts of ideas for sensors and things using nanotubes. So another exciting thing to look at online. Now, material that is a little bit less exciting maybe has two allotropes is oxygen. So oxygen gas is O2, but also there's the oxygen molecule, which is O3, so another form of oxygen gas. Okay, so we're not really covering antimatter very much, but what is antimatter? Well, it's the opposite of regular matter in terms of charge, mostly. So what we've got here is antimatter atom. And the thing is that if you look at it, it looks a little bit different. It's got positive electrons. Well, those are called positrons. And yes, they really exist. And in the nucleus, you'll notice it's negative. It has negative protons, which are called antiprotons. And it even has antineutrons, although since they're neutral, they're kind of very similar to regular neutrons. But the idea is that you actually have this different set of materials that can be used to make matter. And so if you've ever watched a Star Trek episode, one of the things they use is they have engines that are matter antimatter engines. What are they doing? Well, the idea is that when matter combines with antimatter, then you actually destroy some of the matter. So if you mix 30 grams of regular ordinary matter with 30 grams of antimatter, they will destroy themselves, and you will end up without any grams of matter. The mass will disappear, but you will get energy. And that's the energy that comes out that in the Star Trek universe drives the ships. Okay? So matter plus antimatter become energy. And that, of course, is according to Einstein's equation, E equals mc squared, which is saying energy is mass times the speed of light squared. So you've got energy equals mass times the speed of light squared. which is 3 times 10 to the 8th meters per second. And so, yes, so it becomes an extremely large amount of energy from a very, very small amount of matter. In fact, let's do a little calculation just for fun. Okay, so E equals mc squared. And let's say that we had 1 kilogram of matter, just to make the numbers easy. And so that is being destroyed. So maybe we had 500 grams of matter and 500 grams of antimatter, putting them together. Okay, then we would multiply by the speed of light. And square it. So what would that be? Well, 3 squared is 9. 10 to the 8th squared is 10 to the 8th. And then squared is when the exponents are going to add. So that's going to be 10 to the 16th. And the units will come out to be joules of energy. Is that a lot? Oh yeah, that's a lot, right? It's a 9 with 16 zeros. This is a huge amount of energy. And so you could run your house for thousands and thousands of years on this much energy. Okay, so this is a huge amount of energy. So this is what happens in the sun, except that happens a small amount of energy from a fusion reaction is turned a small amount of mass is turned into energy in the sun every time hydrogen gets fused into helium. So, if it was matter antimatter engine, definitely could drive that starship. Okay, we're going to break off now and then go to chapter 12.